Hello, and welcome to week 9. Now that we've investigated geologic maps, you know all about the different sediments and rock types, and you've also considered geologic time. We're going to dive into investigating the geologic history of Minnesota. So with that, let me just go to the slides. Okay, so as I've just mentioned, this involves integrating the knowledge you have and you've built up of sediments, rocks, maps, and geologic time. So you may want to have out a bedrock geology of Minnesota map, but if you don't have it to hand, we'll be coming back to this at various points. So we're going to start at the beginning, so to speak, and consider what cratons are, look at Archean rocks, and then we're going to move through looking at Proterozoic rocks. And remember, Archean, Proterozoic, and Phanerozoic are terms for eons in geological time. And then we'll briefly consider the youngest time chunk, although we're not going to be investigating that until we look at aggregate, that's sand and gravel resources. So with that, let's advance. So first of all, wait a minute, this is, okay. So first of all, let's just deal with a concept or a term that you may not be familiar with. This is the term craton. So all continental landmasses are called by cratons. And these are amalgamations of really old continental crust. And the rocks that form these cratons developed early on during Earth history. And so that includes the Archean and Proterozoic. Now, the thing you need to remember is cratons are these stable central masses within a continent. They're usually composed of igneous and moderate to high grade metamorphic rocks. Now, how did all these pieces that make up the cratons get joined together? Well, they're a consequence of early plate tectonics. And the naming of these cratons gets complicated. If you look at a map of the entire African continent, there's a bunch of different cratons there. We're going to focus on the North American craton. And if you look at this map of North America, or part of it, you can see Hudson Bay here and beloved Lake Superior right in here where my cursor is. And the cratonic rocks that form the core of the North American continent are shown here in these red, brown, and some purple colors. Now, terminology always gets complicated, and the term North American craton often gets used synonymously with Canadian shield. And the North American craton also gets referred to as Laurentia. Basically, geologists have named these continental blocks, and the North American craton gets called Laurentia. Okay, so let's start by looking at the history of the North American craton. If you hadn't already guessed, yes, this is complicated. Now, first of all, these rocks range from 4 billion years to almost 1 billion years old. And something I forgot to mention last week when we looked at geologic time is that the abbreviation GA gets used for billions of years, giga-annum. So the core of the North American craton is called the Canadian Shield. And essentially, it's made up of rocks that range from 2.7 to 2.5 giga-annums, or billions of years. And as I've mentioned, it's made up from amalgamated continental blocks and the oceans that separated them. Those oceans have all the sediments and basement rock, in other words, basalt in the ocean, got squished together during or when they were at convergent plate boundaries. Now, there are 4 main sub-provinces. I told you it was complicated. And these get called the Wabigoon, Quetico, Wawa, and Minnesota River Valley provinces. And they're all separated by major faults. Now, down at the bottom here in red is a really good link, a URL that I highly recommend you go to read a bit more about this. So we're going to start by thinking about the Wawa and Wabigoon provinces. So the Wabigoon province is way up here in northwestern Minnesota. So what you need to remember is we're talking about rocks that are, for the most part, buried beneath the sediment that characterizes the landscape up here, although they are locally exposed. Now, okay, that's the Wabigoon subprovince. And then down in here, these heavy lines of faults, is the Wawa province or subprovince. And really, quite honestly, you don't need to worry about whether it's a province or a subprovince. Just call them provinces. And you can see there's actually several internal faults within that, but it's, again, one whole chunk that is kind of affiliated with each other. There's 3 main zones, if you like. Now, what makes these 2 provinces up? These are what we call classic granite greenstone belts. And that means they're composed of metamorphosed volcanic sediment that loosely gets called greenstone. That's a whole complicated separate topic. Essentially, it refers to sedimentary and volcanic material that includes chert sediments and extrusive volcanic rock that have largely all been metamorphosed to greenschist facies. Remember, metamorphic rocks. And then these greenstones have been intruded by granites. So these make up our classic granite greenstone belts. And the banded iron formation of the Sudan mine in the Vermilion Range, way up here, arrowed in green, is part of the Wawa province. And this also gets called the Wawa Abitibi province because it kind of connects and extends to a province in Canada called the Abitibi province. So the area between Tower and Ely, where the Sudan mine is, has banded iron formation that is part of this greenstone package of rocks. So that's 2 of those pesky provinces. Now let's look briefly at the Quetico province, and it's arrowed in here. It kind of slips in between the Wabigoon and the Wawa. And the Quetico province is essentially a former sedimentary basin that lay between the rocks of the Wabigoon and the Wawa. And it is also intruded by granites. So when you think about each of, well, the Wabigoon and the Wawa, essentially we're talking about complex sets of volcanic arcs that produced volcanic material that all got squished together. Now, and then here there was seafloor with sediment on top of it that got squished in between those two when everything was being compressed. And again, there's a really good URL down here that has more explanation. And finally, the fourth province, the Minnesota River Valley province, way down here to the south. Now, this is separated from all the others by a major fault, the Great Lakes Tectonic Zone, GLTZ, here. As I've mentioned, it's divided into 4 distinct regions. It's kind of complex, but essentially it's made up of really old gneisses, 3.5 billion year old gneisses. And the Morton gneiss is a good example of that. Those gneisses were intruded by granites, and then these rocks were all affected by what we call the Panochian orogeny. And that's a mountain building event that took place at about 1.85 billion years ago. So one thing you may be wondering here is, well, how these are actually much older than some of the rocks farther to the north. And yes, you are correct. So one of the big issues is understanding how these blocks of cratonic rock got smushed up against some younger material. And that's one of the big questions that ties into just how continents are gradually built and how everything has moved over time. So let's jump now to our beloved bedrock geology of Minnesota. So don't worry about the Sioux quartzite yet. We're focusing over on the right. So what I want you to notice is there's an area up in the northwest. This is the Wabigoon. And what you can see is it's green with the red lines for iron formation. And then there's a whole lot of pink. That is the granites. Then largely in blue here, we have the Quetico. So that is, if you look down here, grey-wacky. And remember, grey-wacky is a funky word for a particular kind of sediment. And schist-rich migmatite. So that means migmatite, that's partially melted rock. So it's really been metamorphosed. Then we go down to another one of these granite greenstone belts, the Wawa, or the Wawa Abitibi. And once again, you can see that it's made up of volcanic sediments, plus in pink, those are the granites. And then we move south here, and in this kind of, I don't know, pinkish brown color here that's kind of distributed over much of central and southwest central Minnesota is this Minnesota River Valley province. And you'll see on the correlation of map units, that's way down here. It is old. Although there are older rocks further to the north too. Now, so we've located our cratonic rocks and the material that is kind of peripheral to that. But if we look at our correlation of map units, one unit we haven't dealt with yet is the Sioux quartzite. And I want to touch on that now. The Sioux quartzite in pale yellow is shown here in southwestern Minnesota. Now, Sioux quartzite is fascinating. I'll just call it enigmatic because it's really hard to understand the conditions that produced more than 3,000 feet of quartz sand. It's a pink color, so there's iron that has oxidized in it, but essentially it is a quartzite. It is about just over 2.3 gigaannum, 2.3 billion years old, or you could say 2,280 million years old. So it's old. It's not quite as old as all the other materials. And I know we haven't addressed the anemone group yet. We're getting there. So about the Sioux quartzite again, it's interbedded with a mudstone or shale called catlinite. This is the rock that makes up the sacred pipestone that you can see really well if you go to Pipestone National Monument. I thoroughly recommend a visit there. The Sioux quartzite correlates with several other quartzite units in the upper Midwest. For example, the Barren quartzite in Wisconsin. The Sioux quartzite is also amazingly exposed at the Jeffers petroglyphs, and I thoroughly recommend a visit there. You can see all sorts of sedimentary structures, as well as the incredible petroglyphs, and you also get a sense for some of the quaternary landscape development. So that's the Sioux quartzite. Now, we're going back to fill in a little bit of a hole. So I mentioned the Panokian orogeny. First of all, these are weird words. The word Panokian is just the naming of this orogeny. The word orogeny refers to a mountain building event, and the rocks produced by that mountain building event, even if they are no longer big mountain chains, are called an orogen. So the Panokian orogeny was a mountain building event that took place between 1.86 and 1.83 billion years ago, GA. So, and just to put that in perspective, the Paleoproterozoic, the old part of the Proterozoic, goes from 2.5 to 1.6 gigaannum, or billion years ago. Now, let's just think about where it's represented. So prior to this Panokian origin, there was a passive margin. So all the rocks that are Archean had been smushed together, and there were probably mountain chains, but then an ocean basin started to open up. And that was one of those passive margins, kind of like the east coast of the US. And there was kind of like an mid-Atlantic ridge underneath it, etc. So you had a sedimentary basin, and there were the sediments that make up the banded iron formations of the Mesabi, Cuyuna, and Gunflint ranges were deposited. Now, what then happened was the sediments in that ocean basin were subducted towards the north, and a big island arc, and the details of this are still being worked on, formed. So, and we know that in association with that subduction process, there's going to be volcanic activity at the surface and then intrusion of igneous rocks deep down. So, what happened during the Panokian origin? So, this whole gray area in here is the Animikie group. And the red part of it is iron formation. So they are thoroughly integrated, if you like. So what happened then was that all started to get squished up, and there was a lot of granite intruded. And it's a bit hard to tell, but there's a slightly more lavender pink here that is just sort of, it's just after the sediments were deposited. So we had volcanic activity, and then this incredible suite of granites that we call the Central Minnesota batholith that intruded. So everywhere here, extending into Wisconsin and further to the east, we have this Panokian origin, and this represents huge mountains. We're talking about mountains that are on the scale of the Andes, maybe as much as the Himalayas. This is an enormous batholith, or you could even think Sierra Nevada if you want to try and bring it closer to home. And that mountain range has subsequently been eroded and planed down. So we have now considered, if we looked at our Minnesota geological map, we've looked at Archean, we've looked at the Paleoproterozoic, and coming back to the Sioux Quartzite, one of the enigmas about the Sioux Quartzite is, what is it that caused such a pure sediment? A lot of you ask questions about, if we have a lot of quartz in the sediment, does that mean that it's been transported very long distances over a very long period of time? Yes, you are absolutely right. We can say that about the Sioux Quartzite. Understanding the fine-grained sediment in between the quartz units, that's actually very interesting. There's evidence suggesting that that could be fine-grained volcanic ash, or based on some work one of my students did, the catlinite carries a signature of volcanic ash, and trying to put those two together is a difficult thing to understand. Okay, so what's next? As we look at our Minnesota geological map here, we now move into the time chunk that we're calling the Mesoproterozoic. So that's the middle of the Proterozoic. And what you can see is it identifies the rocks as being part of the Keweenawen supergroup. So what is this? This represents an event called the Mid-Continent Rift, which is when the continent tried to split apart, much like the East African Rift Valley is opening up today. Now, this rift failed. Otherwise, we would be sitting right here on a beach, which may sound attractive, but then we'd have to be dealing with sea level changes. Anyway, I digress. So the Keweenawan Rift was a failed rift. This happened about 1.1 billion years ago, 1.1 GA. Now, this failed rift extended from Lake Superior down to the south-southwest, and then also to the south-southeast. Now, what happens when you have a rift? At the very beginning, when you're melting bits of continental crust, you have what we call bimodal volcanism. That means there's some rhyolite and some basalt. But then over time, it becomes dominated by basalts and gabbros because you're starting to open up some kind of ocean basin. Well, because this rift failed, and we don't know exactly why, there was effectively this depression on the landscape that sediments then started to fill in. So looking over here at the map, where is this? If you go to, well, first of all, look where the red arrow is here. We've got these three colors. If we go to Taylor's Falls, that's Interstate State Park, at Taylor's Falls, you can see the basalts that underlie a bunch of the sediments. So the pinkish brown is the sediments, and then there's the basalts there. Once you get onto the North Shore, all the state parks along the North Shore display in absolutely amazing outcrops, various aspects of the rocks of the mid-continent rift. Anywhere you go up there, you will see rocks that are related to the mid-continent rift. Now, before we move on, I have to address something. Lake Superior fills a depression. Now, what happened much more recently than this, during the Pleistocene, 2.6 million years and younger, was that ice tongues from the Laurentide ice sheet up in Canada advanced south, and they ended up excavating areas that were slight lows on the landscape. So the area that had once been this rift that was still slightly lower on the landscape, the ice really took advantage of that, and it just gouged it out. So what I want you to remember here is that the Lake Superior wasn't as deep as it is now prior to ice advance. The ice did a lot of excavating of Lake Superior and the other Great Lakes for that matter. So let's move closer to now. So now we're moving into the Phanerozoic. So the Phanerozoic is about 540. Technically, it's 538.8, but 540 works. Million years ago until now. So just remember that this is the youngest of the 4 eons that geologic time gets chunked into, starting with the Hadean, then the Archean, then the Proterozoic, and then the Phanerozoic. And what do we see in Minnesota? There are really 3 main time chunks that are represented by or in Minnesota. And if we move over here to a correlation of map units, we can see we're now moving up into the Paleozoic here, and then into the Mesozoic. There are also some Cenozoic sedimentary rocks or sediments, but we'll mention those later. So there's a really good link to Mesozoic geology here. This is at the Minnesota Geological Survey website. Okay, we're going to start by thinking about the Paleozoic sedimentary rocks. So these are Cambrian, Ordovician, and Devonian in age. And as you can see from the map here on the right, they are the bedrock in southeastern Minnesota. Now, what's beneath them is going to be some kind of basement that is probably related to some of those much older rocks that we talked about. And the rocks of the mid-continent rift. So here we are, these sedimentary rocks, Cambrian, Ordovician, and Devonian. And what do they represent? So there was a shallow sea extending across southern Minnesota with sediment being supplied from an area to the east and northeast. And what was happening was there were rising sea levels and then falling sea levels. And that, together with variations in sediment supply, ended up controlling what was being deposited. So we have a mixture of sandstones, siltstones, and limestones. And the cross section that you see down here at the bottom goes from A on the west through to A prime on the east. So we're looking to the north. And what it shows is, well, it just lumps whatever they're deposited on into Precambrian. But here you can see that there is this kind of what's now been slightly folded into a kind of scoop-shaped pattern. There's a fancy word we use for that. And here it shows you the names we use for all these sedimentary rock units, going from the Mount Simon Sandstone, Eau Claire, Wanawak, St. Lawrence Tunnel City, Jordan Sandstone, Prairie du Chien, St. Peter Sandstone, Platteville and Glenwood, Galena, Maquoketa, and the Cedar Valley Wapsipinicon. So that's just so you know that that's how we pronounce all those things. And what you can also appreciate is for much of the area, not all of it, because there is actually amazing exposure of these rocks at various locations in southeastern Minnesota. There is a lot of glacial sediment and soil. Usually that is in the upland areas. The places where we get to see these rocks are usually on the steep valley sides in southeastern Minnesota. This is a really good summary of what controls deposition in these shallow seas. And these diagrams were taken from this source. It's another one of those Minnesota at a glance publications. So if you want to follow up on this, go there. Now, moving forward in time, getting younger, Jurassic sediments. So these are only known from drill core. So that's when we drill down. There was some kind of investigation in northwestern Minnesota, and there were several drill cores obtained. And there's some sediments up there that are Jurassic in age, known, and very little is known about them. So also, there's another link here where you can go and find out what little is actually known about them. Now, the Cretaceous gets a lot more interesting. So at that time, look over to the map here. There was what we call the Western Interior Seaway. And this essentially separated North America into a western and a kind of goofy eastern portion. And this was a transitional marine to non-marine seaway, or you can think shallow sedimentary basin. And there were some Cretaceous rocks deposited on Minnesota basement. And there's really three areas where we find them. In southwestern Minnesota, the sediments correlate with those in South Dakota. There's the Pierre Shale, the Dakota Shale, other fine-grained sedimentary units. If we go to northeastern Minnesota, there's a unit that's called the Coleraine Formation, and it's made out of conglomerate, sandstone, and shale on top of, get this, an unconformity on Precambrian bedrock. So remember, unconformity is a line or a plane on the surface that may be irregular, that represents a period of time for which there is no rock record. So once you get up there, this unconformity represents a whole bunch of time. So what about the Coleraine Formation? Well, it's particularly interesting because it contains conglomerate, but it also contains some fossil clams, snails, shark teeth, and some crocodile parts. And you can actually see it at Hill Annex Mine State Park. And here is an image of the Coleraine Formation taken from the MGS website. But you can see here that there's some fossils. These are ammonites in the Coleraine Formation. Where else do we see Cretaceous sediments? In southeastern Minnesota. There's really weird, slightly iron-rich clay and pebbly sandstone. And these units go by the name of the Windrow Formation and specifically the Ostrander member. And these are regarded as deep weathering, chemical weathering, and probably some physical weathering of the bedrock. So that's our Cretaceous sediments. Then we move into the Quaternary. Okay, so the Quaternary is the time chunk that goes from effectively 2.6 million years, technically 2.58 million years according to this time chart, but as you already know, I hope, depending on the source of the information, these numbers might not agree exactly, and I've simplified 2.58 to, or reduced it to 2.6. Anyway, the Quaternary is divided into the Pleistocene, which goes from 2.6 million years to 10,000 years. Oh, goodness, my numbers don't match at all here. That's interesting. I'll have to double check on this. Anyway, that's the Pleistocene. And then we have the Holocene, which is basically everything from 10,000 years, maybe 11,000 plus years, depending on which time scale one's using. So what happened during these two time chunks? Well, during the Pleistocene, we had the advance and retreat of ice from the Laurentide ice sheet. And this wasn't just one simple advance and retreat. There were multiple advances and retreats. Each time there was erosion, deposition, landforms got made, landforms got destroyed, etc., etc. And that all happened as a consequence of deposition and erosion by both ice and meltwater streams. Now, we're going to investigate this and glacial settings when we look at aggregate resources during week 13. So that's the Pleistocene. What happened during the Holocene? Well, what's happened then that is probably most obvious to us as we look at the landscape is that the landscape is adjusting to changes in sea level after melting of the ice. And the landscape is also adjusting to removal of the weight of the ice from the landscape. So there's what we call isostatic rebound taking place. The land's just moving up a bit, and then we're getting cutting down by streams into that landscape. So with that done, that's our quick tour through Minnesota geological history. One of the texts, oh, I need to hold it in front of me, that I am putting into your Moodle, not Moodle, D2L, is this. It's a publication by the DNR, and it's quite dated. It came out in the 1990s, but it is still a good reference. It goes into some more excruciating detail about plate tectonics during the Archean and Proterozoic. But I expect you to use this and to refer back to it as often as you can, because it's really one of the better resources out there at the moment. So with that, have fun learning about Minnesota geological history. I'll see you next week.